Hi. So this question is from the May 2010 HL paper 2 and was apparently disappointingly answered by students. So I thought I might cover this in the YouTube channel. So as always, I recommend you to pause the video and try it out yourself. And then in the rest of the video, I will walk through how I would approach the problem. So let's get started. The question says that the circle has a radius of 2 cm with an infinite number of sectors, and the areas of the sectors are in geometric progression. The internal angle of the first sector is theta, and the common ratio between the areas of the sectors is k. And we need to show that theta equals this expression. So we know that the area of a sector in general equals half r squared theta, where r is the radius of the circle and theta is the angle. So for our circle, for the first sector, the area would be half times 2 squared. So 2 squared times theta. If I cancel that, I get 2 theta. And if I were to write down the sectors, the areas of the sectors, it would be 2 theta. And then since it's a GP with common ratio k, and GP is just geometric progression, which is the same thing as geometric sequence. So if I were to write down the sequence, it would be 2 theta and then common ratio k, so you just keep multiplying each subsequent term by k. So you get 2 theta times k, 2 theta times k squared, and so on. So we know that although there are an infinite number of sectors, the sum of the areas must be finite because the area of a circle is finite. So the area of the circle would be pi r squared. So pi times r squared, 2. 2 squared is 4. So 4 pi equals 2 theta plus 2k theta plus 2k squared theta plus so on. And since we know that this geometric series converges to 4 theta, we know that k must be between 0 and 1 because a geometric series only converges when the common ratio satisfies this condition. Greater than, actually it can be, the absolute value would be less than 1. But in our case, areas are never negative, so we don't consider the cases when k is negative. So this geometric series, we know that the sum to infinity of a geometric series that converges equals the first term a over 1 minus r, the common ratio. So you can do the same thing here. The first term is 2 theta, so 2 theta here. And the common ratios are k, so 1 minus k. We can divide both sides by 2. And the question asks us to get theta equals blah, blah, blah. So I think we've got that. I'll just make theta the subject. So theta, multiplying both sides by 1 minus k, you get 2 pi times 1 minus k, which is as required. So that's part A done. So let's move on to part B. Part B says that the perimeter of the third sector equals half the perimeter of the first. And based on this, we need to find k and theta. And bear in mind that from part A, we know that this expression is true and should probably come in handy. Normally, if in the first part we are asked to show something, it's usually used in the second part of the question. So the perimeter of the first sector so the first sector looks something like this, theta with r, so r and r, so r is 2. And this would be S, the arc length, and we know the arc length of a sector equals r theta. So the perimeter would be 2r plus r theta. And we know r in this case is 2, so we can just substitute that. So we get 2 times 2, 4 plus 2 theta as p1. And we know from, well, the first part that the areas of the sectors were 2 theta, 2k theta, 2k squared theta, and so on. And so we know that the areas of the sectors have common ratio k, but so do the angles of the sectors, because the area of a sector is what? Area is half r squared theta. And half r squared, this bit, is constant for all sectors because we aren't changing r. The only thing that changes is theta. And so k is also the common ratio for theta. So for the third sector, we'd still have the smaller with a different theta, but r's will be the same. So r theta here will be k squared theta because it's the third term. So the second perimeter would have k theta, and then this would be k squared theta. So 4 plus, so 2r, 2 times 2, 4 plus 2k squared theta, because this would be r times, yeah, so yeah, this s would equal, well, s3 would equal, this is theta 3 would equal r times theta 3, and we know theta 3 equals, well, theta times k squared theta. So this would be 4 plus 2 times k squared theta 3, so k squared theta. So you have this. So we know this expression is given to be true. So we write that 4 plus 2k squared theta equals half p1. p1 is 4 plus 2 theta. I can cancel this, 2 and 1. So I'll rewrite that. 4 plus 2k squared theta equals 2 plus theta. And I bring all the theta terms to one side because remember from part A we have this and I want to use this somehow. So I subtract 2 from both sides. So I get 2 equals theta minus 2k squared theta. I factor out theta, I get 2 equals theta times 1 minus 2k squared. And then I can substitute in this for theta. So I get 2 equals 2 pi 1 minus k 1 minus 2k squared. I can divide both sides by 2 and get 1. So now I've got a cubic equation. I'll rewrite it as a proper cubic so you can see it better. 1 minus 2k squared 1 minus k times pi, so I'll add that here, minus 1, so there's a 1 here, remember that, I always forget that after cancelling this 1 exists, I always forget this, equals 0. Now this is a calculator paper, so I can just solve this using my calculator. You could use NSolve, but that would only give you one solution. And as this is a cubic, we know that it'll have 3 different solutions. So we need to check each solution and verify whether it's valid or not. And remember from the last section, I said that k needs to satisfy this inequality to be true, because otherwise the geometric sequence wouldn't converge, because k needs to be less than 1 for the sequence to converge and greater than 0 for the areas to be positive. So I just graph this equation. I enter the graph pi times 1 minus 2, well, k squared, but this is f of x, so x squared times 1 minus k. Oh, whoops, forgot the multiplying sign. Always forget that. Minus 1. Yes. Enter. Oh, what? Oh, whoops, sorry. Well, that needs to be, sorry. Oh, it's gone. Okay, I'll enter it again. 1 minus 2x squared. Oh, whoops. 1 minus 2x squared times 1 minus x minus 1. Okay, that's it. Let me double, oh, times pi, forgot that. Times pi. Yes, that's right. I hope. Enter. Let's see what we get. Okay, so we've got this cubic, and I'll write down the 3 solutions. So I can just go to graph, 6, analyze, and then 0, and then find each of the 3 zeros. The first one is minus 0.635, then the second one is whoops, what? Menu 6, 1. Whoa, can't read that. I think it says 0.456. Let me see if I can, yeah, 0.456. 0.456. And the third one, whoops, I'm so bad at using this. Analyze, 0. And the third one, finally. What is it? Well, can't read it. It's 1.1.18. So you can already see that this one and this one do not satisfy this inequality, because this is negative and this one's greater than 0. That's greater than 1. So these are what we call extraneous solutions. So the only valid solution is this one. So we write down k equals 0.4456. So that is our answer for k, and we also need to find theta. So theta I can just find by substituting in k here. So theta, based on this from part A, so I can just find that using my calculator. 2 by 1 minus k, k is 0.456. Yes, and I get 3.41805. So 3 sig fig would be 3.42. So that is our answer for part B. Thank you.